Okay, I still didn't quite finish, but got most of it up. I can talk about it. Well, if you go under course materials, week 6, under materials, I put the study guide for week 1. I made the big note there, or capitalized note there. That's not final. I basically didn't get the last 2 weeks up there, but it's time to finish class, so we'll do that. I guess I didn't need to do that. View page width. What's that? Yeah, week 6, which is this week. All right, so first of all, so I'm going to do multiple choice. I usually don't do multiple choice, but in these larger sections, it allows me to grade it faster. I tried a multiple choice test in my cartography class last semester, and the grades are actually a little lower than normal, so I reevaluated my multiple choice testing strategy, and I think this one is easier. But in any case, I adjust the scores. So the highest score is like it'll be like an 80% around. I mean the average score, sorry, not the highest score. Like that, right? Okay. So I'm going to use the Scantrons. So I'll have a few extra, but it helps if you brought your own Scantron. So it's the one that has 50 questions on the front and back. We're just going to use, there are going to be 50 questions. So we're only going to use the front. And I didn't even finish the sentence because I started doing this. But what this should say is, you should pay particular attention to the materials presented in the lecture. And use the book as a supplement for those portions that are covered. Okay? So I'm going to go through here, and using the test as it's written, I put some of the things that you should study for. So here it says functions or basic operations of a GIS. There was a table that had like 5 of them, and it has examples underneath each of them. I don't know if I should like bring these up as I'm talking about. I am. And hopefully it all gets put up there on the internet. I am recording, trying to upload stuff right now. It looks like most everything is. So last week's uploading, and it's almost done. And I'll upload this right after class. Okay, so that was the question. So what I'm talking about here, the slide is in your book too. No, introduction. Oh yeah, that's when I put them up as PowerPoints. Oh. So this one. So these 5 things. GIS does data entry, data editing, data management, analysis, and output. Those 5 things. This table is, I don't know if the book author cited it, but those 5 things are actually based on a very old definition of GIS by old GIS researcher named Keith Clark. He actually writes the book that's probably most commonly used, but it's like $130. So we didn't use Keith Clark's book. And I thought this book was just as good, in my opinion. It's a lot cheaper. But anyway, Keith Clark's definition of GIS has these 5 things. Sometimes they're called different things, but GIS does data entry, editing, data management, analysis, and output. So you should know those 5 things. You don't have to know all the little things underneath them, but generally, be able to define what data analysis is. And you do notice that I tried to keep, when I presented this in class, I said, this is the first part of the course, this is the second part of the course, and this is the 210 course. But anyway, we did attribute query today, which is in the second part of the course, but it's kind of a fine line between data management and analysis. So attribute query, anyway, it's kind of a side note. We're talking about zest right now. Okay, so know those 5 things. Those are the functions or the basic operations of a GIS. Some people could call it the definition of a GIS. But you do need to know that table, or the headlines in that table. All right. Also, just what is GIS data? Basically, it's data that contains spatial data, in other words, where data tied with attributes or what data. And you need to know how it's organized in the broad sense here. This was the very first day of class. We talked about layers, a GIS layer. It's a thematic element of data. It's how data in a GIS system is grouped together. And as we talked about today, typically layers translate into tables. Okay? Sometimes there's multiple tables for each layer, but typically what we're talking about, these tables are tied to spatial information. Okay. Now, we did talk about how GIS is sometimes thought of, I'm going to define it here, as a combination of hardware, software, and people, skilled people that are doing the job. So GIS system contains hardware, software, and people. All right. And then we talked a little bit about why GIS is so great. And that's because it's spatial. It's like a pun. Spatial kind of sounds like special. But it's very, it integrates things really well, because we look at the world and we look at the data and how it exists in the world, how it's related to other things spatially. And spatial actually means having to do with space, not outer space, but just how things are related, connected to each other. And that's the thing that GIS really helps with. Helps us to do analysis that is spatial. We haven't actually talked about spatial analysis up to yet, but that's what we do right when we get back from the break. Okay. So yeah, there's only one more week, and then there's spring break. So that's what I mean by the break. And I'll be teaching from the coast that week. The week we come back from spring break. Just because I'm flying in, landing at Gulfport at 10 o'clock that day. But I do like to come down to visit Gulf Park campus at least a couple times. Last semester I had a situation where there were actually more people on the coast than there were up here, and I visited, I think, 4 or 5 times that semester. But we probably won't get that high, but I'll always visit Yale a couple times. All right, so we definitely talked about coordinates and map projections. So, like I said when we went over this, there are a lot of kind of maybe to some people mundane topics, but they're important because we talk about how we store the where information in the system. And so here's a couple of things. I tried to answer some of these questions, but I'll try to answer even more of them right now. So first of all, an ellipsoid versus a geoid and the Earth's surface. Each of these have a slightly different meaning. So let's actually start with surface. Surface is the real surface of the Earth. It undulates. We can go walk across it, right? Okay. So obviously that's really hard to store that real surface in there without going and collecting data. It's not like a wall-to-wall surface of the whole Earth. It's kind of the purpose of the GIS is to make data layers that represent the surface. So when we want to store information about a coordinate in all 3 dimensions, x, y, and z, we need to come up with a way to determine what that coordinate is. So we can create a mathematical model of the Earth approximation of the Earth. That's an ellipsoid. A geoid is another measured value of the surface of the Earth, and it's the elevation at which gravity reaches like an equilibrium. So where the gravity is equal to mean sea level. So it's of less importance. So basically, for our purposes, we're either trying to measure the actual surface of the Earth, or we're using an ellipsoid to describe the Earth as a modeled. It's not an ellipse; it's a rotated ellipse. It's a modeled thing. Sometimes we model the Earth as a sphere. In that case, we call it spheroid, but it's the same thing. Okay? An ellipsoid and a spheroid. A sphere is perfectly circular, and the ellipsoid is just flat. All right. So what are coordinates? Coordinates help us to identify a location. So they're numbers that guide us to a location on the surface of the Earth, or on an ellipsoid, actually. Which is on the Earth, but it's a model position. Okay. So, spheroid, geographic coordinates versus Cartesian projected coordinates. This really gets into questions that are later on down here. The difference between geographic coordinates and projected coordinates has to do with what makes up geographic coordinates and what makes up projected coordinates. So, geographic coordinates are latitude and longitude. They're referenced from the center of the Earth. Angles referenced from the center of the Earth. So the only thing that is needed to come up with a geographic coordinate system for the Earth is the ellipsoid. Okay? And the ellipsoid is based on a datum. So the word datum actually just is the singular form of the word data, technically. So data is a plural word. Datum is a singular. So the only thing that's required to define an ellipsoid is a data point, or the singular form of data, the location of the center of the Earth, okay, and how big that ellipsoid is defined. Once you define how big it is, what its radius is, and where the center of it is the datum, then you've got a geographic coordinate system. You can reference everything else as an angle off of that. Okay? All right. And then this has to do with these angles. These angles are measured in degrees. And then smaller units are minutes and seconds. There's 60 minutes. So there's 360 degrees in a circle. There's 60 minutes in a degree. And there's 60 seconds in a minute. So, I mean, that's what I mean by that. We'll get to that in a second. Come up to that in a second. So, projections. Okay? What defines a map projection? I'll get to it right now. So, with a map projection, you still need to know everything you need to know for a geographic coordinate system. But a projected coordinate system is taking the Earth and making it flat. And so, when I say developable surface, I'm not sure if I used that term. I know I didn't use it on the test. I'm not sure I used it in class. But the developable surface is how that flat surface intersects the Earth. We talked about that a little bit. So you need to have the ellipsoid, the model of the Earth, and then the flat surface is draped over the Earth somehow. Whether it's a cone, I know we talked about that in class, whether or not it's a cylinder, or it could be a flat plane. And it touches the globe in some places. And how it touches the globe, in the places where it actually touches the globe, there's the least distortion, because we're projecting that round surface onto the flat surface, whatever that surface is. Okay? So we're projecting the ellipsoid onto the developable surface, the flat surface. Okay? So in order to define a map projection, you just need to define the ellipsoid, and then there's a number of different parameters that you need to know to define how that circle, and you don't need to know like all the different things, but you should know that those three types of map projections are using a cone, a cone, a cylinder, or a flat piece. So that's on the test. And then how that cone fits on the Earth. Basically, where it touches the Earth, those lines of tangency are where it will be the most accurate. So where is it the most accurate? And finally, you need to know the units. All right. Why do we need to use map projections, or why do we use map projections? Because they allow us to measure distances and areas. And latitude and longitude actually doesn't allow us to do that. You can't measure distances and areas directly from latitude and longitude. This is on the test. What are the distortions that map projections can have? Shape, area, distance, and direction. I should put comments in it. Shape, area, distance, and direction. Okay? Shape, area, distance, and direction. In class, I told you that really everything kind of boils down to shape and area. Okay, but oftentimes we put them into each of these categories. So, for example, a Mercator projection, you can take true compass measurements off the Mercator projection, so it's also good. So direction is preserved very well, and as a result, shape is also preserved pretty well. But there are trade-offs. So you need to know, why are some map projections better in some areas than other map projections? Basically, map projections are defined so that they're accurate for the area that's being studied. And as that area gets larger, you're going to lose some accuracy over the whole area. You can make a map where the coordinates can be accurate to within less than a meter if your map area is just a small slice of the world. But as it gets larger and larger, there's more distortion that you're introducing. And then lastly in there, you should know the Universal Transverse Mercator System. What you should know about that is that there are UTM zones throughout the world. You're always in a UTM zone. And that it's a coordinate system that is projected coordinate system. And it can be used anywhere in the world, but you don't want to use it for a project area that goes beyond a UTM zone. It's for smaller projects, relatively. It's not for a full United States of America study about something. The state plane coordinate system, in a very similar way, is a coordinate system that is set up for just the United States, but they're just portions of states. Every state has at least one state plane coordinate system. Our state has two. Lots of other states have 2 or 3 or 4. And then some states that have multiple state plane coordinate systems also have adopted their own statewide coordinate system. In our state, that's called MSTM, or Mississippi Transverse Mercator. All right. Data models and entry. So you should know the basics between the raster data model and the vector data model. Vector is the one that's based on points, lines, and polygons. Raster divides the Earth up into grid cells. Okay. Topology is a data model that allows for relationships between connected objects to be stored in the database. So like if you change the boundary between two polygons, it will tell you if topology is preserved, it'll tell you that that you're moving the boundary rather than just adjusting the boundary and leaving a gap in between. Raster and vector data formats. Oh, here, what I mean by this is that you should know, and there was a slide that talked about this, common raster and vector data formats. So shapefile is a vector data format. File geodatabase is actually can be used for both, but it's more commonly a vector data format. On the slide, it was in the vector data format category. Raster are just like image files. A TIFF or a JPEG are several of the raster data formats we used, or we talked about. In class, you use the IMG format, which is an Erdès Imagine data format. Okay, then we went on to digitizing. We talked about some of the pros and cons. There was a slide on that, particularly the sources of error from digitizing. And then there was a little slide that showed map parts, so the parts of a map, a legend, neatline, the data frame itself. Just know those. It's on a slide in one of the lectures. And then we talked about during digitization, we talked about this concept of map scale and how a GIS system doesn't inherently have map scale because you can zoom in and zoom out. However, when we digitize existing maps, or really when we get data from any data source, there is an inherent grain size associated with that data, a level of granularity. So you do need to keep that in mind when you're using digital data. And we revisited it again when we did talk about digital data. That however that data was created, if that line for that river isn't detailed enough for the analysis you're doing, it doesn't matter if you zoom in really far. At some point, that data could have an inappropriate grain size. So if you're using existing digital data or you're creating it from an existing map, you need to think: is this map appropriate for what type of analysis that I'm doing? All right. Then the next chapter we talked about was this was week 4. We talked about georeferencing, GPS, and remote sensing. We talked about all 3 of those. I'm going to tell you right now that I glossed over remote sensing. I didn't talk about it much. I made a few remarks about it. We have a whole course in remote sensing. So this isn't really the venue for teaching a remote sensing course. I did not include any real test questions about remote sensing. Okay? If I do put anything on there, it'll be like, what type of data is remote sensing getting, a raster or vector, something like that. Okay? What's an image? Something easy like that from the lecture. But right now, I don't have any questions on that part. So it's basically the georeferencing and the GPS lectures that we do have test questions on. So we talked about coordinate transformation. And when we did that, we brought up a few topics, and these are definitely on the test. So we talked about root mean squared error. Okay? So it measures how well your 2 data sets are matching up. So you usually have a data set that's already in a geographic, in a coordinate system. It may be geographic, it may be more likely it's projected coordinate system. And you're lining up your data with that data that already exists in a coordinate system. And the RMSE, you don't need to know how to calculate it. Okay? What you need to know is what it tells you. It tells you how well those 2 data sets match up. What are the units? The units are in the same units that your map is in. So if your units are in meters, whatever coordinate system your units are in, it's in there. So if it's it's in meters, it's in meters. If it's in miles, it's in miles. It's less likely. It's usually in either feet or meters for most data sets. Okay? So it measures how well those two match up from the control points you've provided. Typically, ideally, you want that to be, like if you're dealing with raster data, you want that to be somewhere around the same size as a pixel. If your pixels are 3 meters, you want your RMSE to be. It doesn't always happen in the real world, but that's what you want. And typically, like when you have a really high RMSE value, you can look at the residuals and find out which of your ground control points are better than others, and see if there's a reason why one of your ground control points is way off. All right, one or more. What does the first order transform correct for? So typically you're going to use a first order transformation. And this is the part in the lecture where we said, okay, the first point that you add translates the image that you're trying to correct onto your other data. It translates it. It puts that point in the right place. The second point that you add, actually, I put them in the wrong order, but there's no order on the tab. Second point rotates it into the right place, and the third one scales it. So the first order transform will rotate, translate, and scale your data. So you need to know that. Okay? You don't need to understand the math behind it, other than the fact that the math isn't really that hard. It's just like any other equation, like if you've taken a statistics class where you're predicting a number based on another number. It's regression. It's just basically got two unknowns, an x and a y, instead of just one unknown. All right. Translation, scale, and rotation. Those are on the test. Okay. What makes a good ground control point? You need to know that. So ground control points actually have to be on the ground. That's important. Typically, you don't want a ground control point on a building or in a tree. The ground control point has to be easily identifiable, something that you can pick out in the data really easily, and you can define it down to like a pixel. It can't be like a ground control point couldn't be a whole car. I mean, you can, well, it shouldn't be a car anyway because that's not on the ground, but the point is it should be a really precise thing where it probably only exists in one pixel. And then finally, your ground control points need to be well spread out throughout your imagery. They shouldn't be clustered. All right, segments of GIS. You've got the control segment, you've got the user segment, and the satellite segment. Okay, so those are the 3 segments of GIS. So this is kind of a new topic. This is a new chapter in the book. Okay, the number of satellites here. You know, I think I gave you 2 different numbers in class, 30 and 27. You just have to know that it's not like 100 and it's not like 5. Right? So roughly, you know, there's a number of satellites up there, and they actually do change from time to time. They launch more satellites, but they try to keep. I mean, they actually need. I forgot whether it's 26 or 27 in order to have it operational, but they usually have a few more so that they can always have enough. Right now, the lecture says 30 is the number that we have. But it has to be in the upper 20s in order to operate. What's that? The control segment, the user segment, and the satellite segment. It's not exact. The slide in the class says 30. I think I said 27, but then like 2 slides later, it said 30. And there are different numbers at different times. I could look it up. It's the numbers in the high 20s for it to operate correctly. I'm not going to ask for an exact number, but there's going to be a number of satellites, and you need to know that it's not 100 and it's not like 5. So maybe the question is, which of these numbers is closest to the number of GPS satellites currently And 30 will be one of the answers. All right. So the sources of error is you're going to look at that. So there are a few different sources of error that we talked about. I'm not even sure I'm going to get all of them right now, but I know that I talked on the test about multipath. So multipath is when you're too close to a large object. And oh, did I skip something? Yeah. How many do you need to get a position? The answer is 4. How does it work? It works through taking range measurements to these satellites, distance measurements. So you basically know that you're a certain distance away. And the way that that distance gets created is through travel time. So the receiver is able to make an estimate of the travel time of the signal from the satellite to the receiver, and it knows the position, so it's actually trilaterating its position. Okay? Anyway, so sources of error. One of the sources of error, multipath, means that that signal bounced off of something else before it got to the receiver, and therefore the distance traveled is an error. There's an error associated with that. That's multipath. Okay. The book, that's one of the bigger sources of error. The book and the lecture talk about a few others. Some of them are just related. And these are very small portions of the error, but related to the clocks being off and the atmosphere distorting the signal and things like that. Those are lower sources of error. Another larger source of error is what we refer to as the PDOP, and that is how the satellites are aligned for your particular receiver. So if your satellites are all next to each other, they're clustered, the error is going to be amplified. The potential box that you're in is larger. So as PDOP gets higher, it just means your satellites are closer together, and the uncertainty about your position is larger. Okay, so that's what PDOP means. I don't actually think that PDOP, which stands for precision dilution of position, is actually on the test. So not literally what it means. What the letters PDOT mean, that's not on the test. What's on the test is that it's a measurement of how well your position can be estimated based on the positioning of the satellites. And as they're more spread out, you get a more accurate position than if they're all next to each other. Okay? Just like with ground control points, you get a better if they're spread out, you get a better estimate. Whereas if they're all together, you get a worse estimate. And then differential GPS. What is differential GPS? Differential GPS means that you have two GPS systems involved. One is on a fixed known position. The other one is what we call a rover that's moving around. And the one that's on a fixed known position is broadcasting the differences, or the differences from the real position to the known position. Okay? Just as a side note, this isn't on the test, but technically that position doesn't have to be absolutely known. You could set a GPS up there for like 20 minutes and have it because the average position will be more accurate than any given value, and that would still improve the position. Anyway, that's a little bit of a side note. So the position is somewhat more known than the rover position, and it's broadcasting the difference between the absolute position and the measured position at the GPS at that time, because GPS error is highly correlated. In other words, the GPS error here is not much different than the GPS here and here. I'm slowly getting into a place where my GPS error could be more and more off. Typically within most GPS vendors, and this isn't on the test, but most GPS vendors will tell you that if you're within like 5 to 10 kilometers of the position, you can get down to like 2 centimeter accuracy. If you're further than that, maybe 15 to 20%. It's a 15 to 20 centimeter accuracy. Okay, that's as far as I got. What I'm going to do is add in the remainder here, but let me just talk about it really quick. I did kind of mention a few things that would be on the test today. Today's test, obviously you need to know how to construct, and since it's a multiple choice question, you just need to know how to identify a query that involves ands, not like actually what you put in the GPS system, the GIS system, but you need to know like which rows would get selected if I did an and, or which rows would get selected if I did an or, which rows would be selected. So you need to be able to interpret a statement and select the right rows, which is some of the things that we did during the lecture. There isn't too many questions on the normal forms, but there are a few questions that basically just make sure that you understand that a table, it's better for a table to be normalized and be able to identify a dependency in a table. Okay, but as far as like, is this a second order or third order normal? There's no questions on that. Okay, but being able to recognize a dependency in a table is on the test. But I'll go through and make sure that I get everything. I'll finish writing the test. All right, that's the first week, course materials. Last week was the one where we talked about digital data sources. I haven't actually put a lot of questions about digital data sources on the test. And most of this one, other than when we talked about revisiting, data itself. Oops, that's the lab. Talk about this real quick. Bring it up. Yeah, this part right here. We revisited extent, grain, and attributes. So when you use digital data, it's important that it covers your area, that it has an appropriate level of resolution or accuracy, and that it has the attributes that you need. This is something that's discussed. The rest of these, I'm having a little bit of trouble coming up with good questions. Because this is mostly just about getting data that exists on the internet. We talked about digital raster graphics, digital line graphics. We talked a little bit about census data hierarchy later in there. So I'll come up with some questions and throw them into the test there, and put them on I'll put those on the review sheet. And I'll get the review sheet out later today. And so by tomorrow morning, the review sheet will be complete. If you have any questions, you can email me about it, and that should be good. All right. Any questions about the review sheet as it stands? All right. I'm going to go ahead and stop.